So here is an example to illustrate how expected utility theory can be used in practice to solve problems. Here in this example, we start out with an initial wealth W, a probability of loss pi, which is going to be a number between 0 and 1, and then a particular damage amount which will be realized if there is a particular loss event. And the question here is, we're looking to ensure the loss, and each dollar of loss costs Q to insure. And we can buy alpha units of protections. So we can choose to insure $1 or $10 or $20 or however many dollars we wish to insure. And the question, of course, is going to be to choose the optimal level of alpha, how much to insure. So let's consider what would be the wealth of the individual after purchasing the insurance. So if there is no loss, let's first consider a situation where there's no loss. Well, it would be your wealth less how much you choose to insure times the cost of insurance. And then if there is a particular loss amount, your wealth would be your wealth less the cost of insurance less the damage amount, which would now be realized, plus the coverage. How much you insured would be paid out to you as coverage. Now we can assume, of course, that each amount would give you a particular utility level. And there's a probability associated with each payout. In this case here, it's 1 minus pi, and in this case here, it's pi, probability of the loss occurring. So the problem here is to try to maximize the utility of this lottery. Maximize the utility of the lottery, which means finding the optimal alpha, how much to insure, such that the condition that we impose here is that alpha can be positive or equal to 0. Right? So we allow for the possibility that it's actually equal to 0 because maybe insuring nothing is the optimal solution. Now, what is the utility of the lottery? Well, we have to apply expected utility theory, which tells us that the utility of the lottery is simply the utility of each outcome multiplied by the probability of that outcome. So it's pi, the probability of the damage, times the utility of what you would end up with if the loss event occurs, plus the probability that no damage occurs times the utility of your final wealth amount, which is simply what you started with less the cost of the insurance. Okay, so this is how expected utility helps us, because it helps us figure out what the utility of the lottery is. Now, one more assumption here. We're going to suppose that the price of the insurance is fair, which means that the expected cost of the insurance, the cost of the insurance, which is Q, right, is equal to the expected loss, which would be pi, the probability times $1, and then the cost of insurance would be Q times $1. So we assume that Q is equal to pi, so in this entire expression here we can replace Q with pi, which I'm going to be doing here. Okay. So to save some time, I've written out the first order condition. So we have to take the partial first order derivative with respect to alpha of the entire expression, the entire expected utility, applying the chain rule, we have to first take u prime, but then multiply by the derivative of what's inside the utility function with respect to alpha, which here is going to be 1 minus pi, and here it is. And on this side is going to be minus pi, and here it is. And these are simply the probability weights. Now, why does this entire expression have to be negative or equal to 0? Why is this not simply equal to 0? Well, that's to accommodate for the possibility of a boundary solution in the event that alpha is equal to 0, which we've allowed, right? We choose to ensure nothing. Maybe that's a solution. Well, in this case, we see that it would be possible for a first order condition to be strictly negative. And so we combine all of these conditions here into one, where the first order condition has to be negative or equal to 0. Now I have written the first order condition here by simply factoring by pi times 1 minus pi. And I'm also outlining here an additional assumption, which is that we have strict risk aversion, meaning that the utility function is strictly concave, meaning that u prime, the first order derivative, is strictly decreasing. I should have been writing strictly here and I forgot. Let's consider two situations. The first situation where alpha is equal to 0. What do we get? Well, this entire expression here reduces to this, and we can easily see that if pi is equal to 0, or if d is equal to 0, we can easily see that this entire expression here will be also equal to 0. And so the first order condition will be automatically satisfied. So in these situations, alpha equal to 0 is a solution, right? We would choose to ensure nothing if we either had a probability of loss that was null, or the loss would be nothing. That makes sense. But if we assume that pi is not equal to 0 and that d is not equal to 0, then this first order condition can never be satisfied. And that's because this amount here is smaller than this amount. And so because u prime is decreasing and strictly decreasing, this here will be greater than this amount. And so in turn, the difference will always be positive. So this term here will always be positive. So alpha equal to 0 can never be a solution. So we now have to consider the situation where alpha is equal to 0. If alpha is equal to 0, then, alpha is strictly positive, then the only solution here, again, assuming that pi cannot be equal to 0, the only solution would be that this entire term up here is either negative or equal to 0. But because u prime is decreasing, actually the best that we can hope for is that this be equal to 0, because this will never be negative, because this number here is smaller than this number. And so let's consider the situation where this here is equal to this, which is the only way that this entire term can be equal to 0. So it takes us here, and we can easily solve this by simply crossing out here these terms, and so we are left with the solution that alpha be equal to d, meaning that we ensure fully. And so what result have we established here? We've established that if the insurance is actuarially fair, remember the assumption that Q, the cost of the insurance, be equal to the expected value of the damage, be equal to pi. if we assume that the insurance is fair, then the decision maker will insure completely if he is risk averse. So we will insure the full amount of the damage given risk aversion. Now remember that going back to the actual wealth amounts, if there's loss and if there is no loss. So if there's loss, we had the wealth less the cost of insurance, less the damage plus what we insured. And given that alpha is now equal to d, this simplifies to alpha minus dq, which is also equal to w minus d pi. And if there is no loss, this is the resulting wealth, which is equal to w minus dq, since alpha is equal to d, and since q is equal to pi, we also get w minus d pi, which means that in both situations, we end up with the same amount of resulting wealth by insuring fully, right? It doesn't matter if there's a loss or if there's no loss. We'll end up with the exact same wealth amount. Now this result actually makes a lot of sense. You can think about the situation as follows. Here's where you are. Here's your wealth if the damage happens. Here's where you are if nothing happens. The expected value of wealth, given the uncertainty that the loss might or might not happen, is here. And this simplifies to this. And now I can notice that this expression here reduces quite easily to w minus pi d, which is precisely what I get no matter what if I choose to insure, right? Now what does risk aversion mean? It means that the utility of this particular amount could be anywhere here depending on the probability weights, but let's assume that it's here. The utility here this is the utility of w minus pi d is always going to be greater than the expected utility of taking on the gamble and not insuring and simply living with the uninsured possibility that there's damage or no damage, which would be somewhere around here, as expected utility theory tells us. So this is why I'm happy to insure, right? Because if I choose to insure completely, I'm getting this no matter what, and the utility, if I'm risk averse, the utility will be greater than simply taking on that gamble, taking on the risk of loss.